From the chaos on the outer planets to the broiling heat of Earth's closest neighbor, radical weather is the norm in the solar system. We do have our own extremes here on Earth, but they pale in comparison to the fastest, dustiest, wettest, and most brutal alien storms. On Earth, the sun drives our weather, and sometimes drives it wild. When hot and cold collide in the atmosphere, watch out. This is true locally and globally. But storms on other planets are bigger, badder, and stranger than their counterparts on Earth. Why is that? Because of the sun? If not, what else fuels their fury? The basic laws of nature, the rules of the game, are pretty much the same wherever you go in the solar system. But every planet has its own way of playing the game. Right now on Mars, the entire planet is being covered in dust. This global dust storm blocks 99% of the sun's rays from reaching the planet's surface. It's actually a system of smaller but still massive storms churning dust high into the atmosphere. Once it starts, it takes months for Martian skies to clear.
Mars is just the most dramatic weather in the solar system in some senses. It's very rare in the solar system you get a weather event that can take out the whole planet.
So if the basic rules of hot and cold are the same on Mars, why is the weather so different from Earth? For one thing, Mars is half the size of Earth. It's also 50% further from the sun, so it's much colder. The average temperature on Mars is minus 80 degrees. That's almost 130 degrees colder than Earth. And the atmosphere is extremely thin and composed mostly of carbon dioxide. But perhaps the most important difference is this: Mars is a global desert.
What would Earth be like without water? Well, it'd probably have a lot of dust. There's no liquid water at the surface of Mars, and there's very little water in the atmosphere, and so there's nothing to sort of keep the dust down.
On Earth, dust storms are localized and short-lived.
The reason for that difference in scale is that the storms are generating their own weather on Mars, whereas on the Earth, they're slave to the weather that's going on around them.
In other words, on Earth, the global weather system creates dust storms. On Mars, the storms create a global weather system. Astronomers have always been able to see big Martian dust storms easily with Earth-based telescopes. But what they couldn't see was what caused them. That would require a trip to Mars itself. In 2003, NASA landed 2 rovers called Spirit and Opportunity on the Martian surface. Their mission? To learn more about the geology of the red planet. NASA engineers always assumed that as these 2 vehicles roamed the Martian surface, dust would build up on their solar panels.
If you have a lot of dust that's falling down out of the atmosphere and coating the panels, pretty soon you're not getting much sun to the silicon. And in fact, we thought that was what was going to kill the rover Spirit and Opportunity.
Only it never happened. The rovers didn't die as expected. As dust built up on the panels, somehow something would clean them off. But how could this be? NASA engineers were baffled until the rovers themselves saw the culprit. Martian dust devils.
It turns out that dust devils were sort of our white knight. They came along and cleaned off the solar panels just at the time we were expecting to start having some problems.
There are beautiful photos that actually show dust devils moving across the Martian atmosphere and ghostly soldiers moving out there in the distance.
A dust devil is really an extreme form of rising hot air or convection.
And that hot air wants to go up, and it comes up just like, water going down a drain. Well, this is air that just spirals up into the colder parts of the atmosphere.
Whenever warmer air, which is less dense, rises up through cooler air, which is more dense, it rotates as it swirls upwards. Convection can be very powerful, strong enough to lift things up. On Earth, it lifts moisture, and that's how thunderstorms form. But on Mars, there is no moisture, so it lifts dry, dark dust and creates giant dust storms instead. Once airborne, Martian dust clouds absorb sunlight and heat the atmosphere. This supercharges the convection, lifting still more dust.
That produces more winds, which bring up more dust, and these things can spread up to thousands of miles across, or even, in some cases, they can envelop the entire planet.
And because the Martian atmosphere is so thin, it doesn't take much to get this cycle going.
You get a lot more difference between the surface temperature and the air temperature, and so the convection on Mars is very much more vigorous.
As a rule, Earth doesn't get the temperature extremes that Mars does. But sometimes, here and there in the deserts of Earth, convection can be very Martian-like. And we get dust devils, too. But at Arizona State University, Lynn Necrace makes dust devils to order in a lab to study them up close. He uses a vortex generator and substitutes lighter, dry ice for dust. What he creates is not an exact replica of how real dust devils form, but good enough to see how they pick up dust and debris.
Natural dust devils usually form from the bottom up, as opposed to tornadoes, which form from top down. So what happens when we turn this on, we have the airflow starting, and as the airflow starts to rotate from the fans down to the floor, we actually end up having the vortex form.
In other words, the vortex generator, basically a huge vacuum cleaner, imitates the swirling action of convection.
You can see here there's a wider base where larger particles of the dry ice are being swept up and gets wrapped up and tightens as it expands upward. The center of the core is where the majority of the lifting would occur.
Martian dust devils have been helpful, keeping the rovers clean. But could they actually be making a mess of the rest of the planet? Some scientists think there are so many at any one time, and they lift so much dust into the atmosphere, that together they trigger these much larger dust storms.
It starts wind patterns, and the air's warmer over here, and it's colder over here, and the air starts moving around. Pretty soon you're spreading dust over the whole planet.
And we found measurements that indicate there's up to maybe 200 dust devils per square mile per day during some parts of the summer.
And they can range from a couple of 100 feet tall to devils that stretch 6 or 7 miles high.
You can get just towering monsters of dust devils that we would never see on the Earth. The kind of maximum-sized dust devils you see on Mars are more like tornadoes on the Earth, where they're going up almost 10 kilometers. So these things are just real monster systems.
Back at Arizona State University, scientists blow crushed walnut shells as silicate particles in the Planetary Geology Wind Tunnel to replicate dust and wind conditions on Mars.
If we can understand and sort of replicate what's going on, then we can, in a sense, understand how the Martian surface has been changing and continues to change as time goes on.
Oddly enough, their studies reveal that it's easier for winds to loft larger sand particles into the air than smaller dust particles.
This is because there's cohesional forces and static forces between the very small, fine dust grains. We imaged the rover deck and actually found that sand seemed to have bounced onto the solar panels, and we can see the skip marks across the surface. And this is interesting because we don't usually see sand typically reach that high.
Dust devils on Earth never have the punch to produce that kind of chaos here. Lucky for us. But what would happen to Earth if a giant Martian-style dust storm did overtake us?
If you had dust storms of Martian size on the Earth, you would find your city being enveloped in an orange-tan haze.
Air quality plunges as the storm churns. Dust blots out the sun, shutting down photosynthesis. No plants, no food. Temperatures would plummet. 65 million years ago, an asteroid may have struck the Earth, creating these same conditions, wiping out the dinosaurs.
It's not going to happen on the Earth, though, because there's going to be rainfall and moisture condensing on the dust grains and so forth and dropping them out of the atmosphere. So it's very hard for something like that to spread in the climate conditions that we have on Earth.
Forecasting Martian weather may someday be just as important as forecasting the weather on Earth. If we ever want to send a manned mission there,
The word environment no longer really applies just to the meadow next door and the little stream down at the end of town. It's the whole inner solar system. I mean, that's really our environment now.
the sun's energy bathes all the planets. On Earth, it creates hurricanes. On Mars, planet-wide dust storms. But with almost no solar energy, distant Neptune produces violent and powerful winds. Where do they come from? And just how bad are they? If Neptune's winds were to travel to Earth, these alien storms would literally blow us away. The orbit of Neptune lies 3 billion miles from the Sun, at the outer edge of the solar system. There's a lot we don't know about this big blue planet. Neptune's jet stream winds blast as fast as 1,500 miles an hour in its upper atmosphere. But how? The sun controls the weather on Earth and Mars, but it barely reaches out here. No sunlight means freezing temperatures, an average of minus 392 degrees Fahrenheit. So if there's no sun and no heat, where do these incredible winds come from?
One of the interesting puzzles is that as you go further out in the solar system, you get further from the sun, the winds don't go down. You still get very strong winds.
The energy for Neptune's winds must come from somewhere, and scientists are working to figure it out.
Neptune's energy is certainly not going to be powered by solar radiation. In fact, the energy we detect coming out from the planet in the infrared as heat is 2.5 times the energy coming in from the sun.
So the planet is creating its own heat, not from its core, which is made of rock and ice, but wrapped around this icy center is a mantle of ammonia, methane, and water, all being squeezed by enormous pressure and generating tons of heat. So while Neptune is frigid on the outside, on the inside it's giving off a lot of heat. This heat may help generate Neptune's winds, but they're still too strong to come from the mantle alone. Something else is pushing them faster and faster. Earth has a hot core too, and it's a lot closer to the sun. So why don't we have winds like Neptune? For one thing, our oceans store and release energy, and that helps generate our weather.
That adds energy in places, takes it out in others, in a very complicated system.
This complicated system produces a lot of wind. And just where are Earth's fastest winds found? Surprisingly, not over the ocean. They blow instead over the top of a fairly modestly sized mountain. New Hampshire's Mount Washington.
The highest winds ever observed by human beings were right here on Mount Washington at 231 miles an hour on April 12th in 1934.
Mount Washington Observatory, a private, non-profit scientific institution, is responsible for tracking the weather and climate atop the 6,288-foot tall mountain. This remote weather station, accessible only by snow tractor in the winter, has kept daily records for the last 76 years.
It's definitely one of the most extreme locations on the planet. We regularly see in the wintertime winds exceeding 100 miles per hour every few days.
Nowhere near as ferocious as Neptune, yet still pretty strong. But why does this mountain, 1/5 the size of Everest, produce such fierce gusts?
We're at a place where we have winds converging from various directions, coming from the Ohio River Valley, coming down from the St. Lawrence River Valley, coming up the eastern seaboard, all converging here in this area on top of Mount Washington.
The elevation change from the valley floor to the summit of Mount Washington is very significant for any mountain range. It's over 4,000 feet, so air is forced to go over the mountaintop and forced to squeeze in there, and is accelerated as it's squeezed over the mountaintop.
And they measure it every hour, on the hour, 24 hours a day, 7 days a week.
It's blowing over 100 out here right now. Ice is forming on the instruments more quickly. It's time to go up and de-ice the instruments, even though it's blowing over 100. We got to do it every hour now.
Ironically, Earth's uneven surface, which channels winds into powerful gusts on Mount Washington, ultimately knocks them down over time. And this is the big difference between weather on Earth and weather on Neptune. Earth has mountains that slow winds down. Neptune is as smooth as a cue ball.
It's not so much a question of you're driving them stronger, because you're not. It's just that there's nothing to slow them down.
Simply put, once Neptune's winds get blowing, there's nothing to get in their way. So what would an average Neptune wind speed of 850 miles an hour do to us here on Earth?
We have parking level winds in the Earth sometimes above 100 miles an hour. You consider that pretty dangerous. So if we sat with 900 mile an hour winds from Neptune on the Earth, we would probably start wiping out everything on the surface and scraping everything off.
Giant Neptune takes wind and transforms it into something extreme and almost unrecognizable. But orbiting just beyond the rings of Saturn is a small moon that does the same thing to rain. This is Titan, where an everyday rain shower would turn Earth into an explosive fireball. It's a cloudy day, and a gentle rainstorm starts. Here on Earth, you'd grab your umbrella and consider it a minor inconvenience. But this isn't Earth, and it's no ordinary rain. You're on Titan, a small moon of Saturn. And in this chemical downpour, you'd need more than an umbrella to protect you. The rules of Earth weather definitely don't apply here. But Earth and Titan are alike in a lot of ways. On Earth, we have a solid surface, a protective atmosphere, and plenty of water. All these things make life on our planet possible. There's really nowhere else quite like Earth anywhere in the solar system. But Titan comes close. Like Earth, it has a solid surface. And that's not all.
Titan has an atmosphere that's, in general, very similar to Earth's. In some ways, it's mainly nitrogen, like Earth's atmosphere. It's rich with organic material, also like Earth's atmosphere.
But similar isn't the same. Here on Earth, our atmosphere has a huge supply of water in it all the time, constantly evaporating and raining back down, like here on the Hawaiian island of Kauai.
Today we're on the slopes of Mount Waialeale, which is the cloud-shrouded mountain behind us. It rains over 40 feet a year here.
Earth's water cycle starts when warm, moist ocean air rises, forming clouds that eventually condense into rain. The rain falls back onto the land, where it eventually drains back into the ocean, starting the cycle again.
When water evaporates, it absorbs solar radiation. When water condenses, it releases all that energy into the atmosphere. And this transfer of heat helps to moderate conditions on Earth.
Earth's water stores as much as 80% of the sun's heat, helping keep our temperatures steady from the equator to the poles. Scientists theorize that Titan might have water or some other liquid that might produce a similar effect. And in 2004, when NASA's Cassini probe visited Saturn, it found some pretty good evidence to support that idea.
If you went to Titan and you were looking at the landscape, you would see something that in some ways would look almost familiar to you. You might see big mountains and valleys that were carved out by running liquids.
In fact, as Cassini flew past hazy Titan, its radar read the surface below. Scientists saw channels cutting across the surface, much like rivers on Earth do. Some as long as 900 miles. The first strong evidence of liquid on Titan.
There are large bodies of liquid on the surface of Titan. Nowhere else in the solar system except for the Earth are there any large bodies of liquid.
Could water, the liquid that carves Earth's mountains and valleys, also be carving these features on Titan's surface? Or could it be something else? The problem is that Titan is too far away from the sun. If it was water, it would be frozen solid.
It's about minus 300 Fahrenheit on Titan. So things behave very differently on Titan than on Earth. Because it's so cold, methane, which is a gas on Earth, is a liquid on Titan.
One mystery solved. But just because methane is a liquid on Titan's surface doesn't mean it's part of a weather cycle like water on Earth. So how do we know that this methane also falls from Titan's sky? That answer is shrouded in mystery, literally.
Titan is completely covered in a thick haze of smog particles, like a very, very bad day in Los Angeles.
Despite the haze, the Cassini probe once again revealed the answer.
We can see the upper clouds, and we can see evidence for rainfall because the clouds drop very precipitously. We hypothesize that we're seeing the effects of rainfall.
Methane rainfall.
We think that Titan has methane monsoons. So we think that sometimes Titan has a lot of rain that is able to carve rivers and leave large fluvial deposits on the surface.
Cassini's radar imaging also revealed large methane seas on Titan's surface.
If you have liquid methane on the surface, in a lake, for example, that methane can evaporate off and become methane gas in the atmosphere. So you have kind of a cycling of methane between liquid phase and gaseous phase and between the surface and the atmosphere. That's very similar to the water cycle that occurs on the Earth.
But methane is a flammable gas. So why isn't Titan on fire?
For any combustion, you need two things. You need both a fuel, which methane is, but you also need oxygen. And on Titan, you lack the oxygen. So the whole thing is basically a big fuel canister, but there's no oxygen with which to burn it, and so it's all very stable.
If it were cold enough here on Earth to produce methane rain, the oxygen in our atmosphere would create a worldwide firestorm. Luckily for us, that can't happen. Titan's methane cycle makes it both alien and familiar to us.
To me, Titan is very exciting because all the materials are so different, and yet these processes produce very similar landscapes to what we see on Earth.
Titan proves that where alien weather is concerned, looks can be deceiving. On Jupiter, it's all about size. Drop the great red spot onto our world, and it makes even our worst hurricanes look like a breeze. This is the biggest and oldest storm in the solar system, and Jupiter's most famous feature. It even has its own name, the Great Red Spot.
It's about 2 or 3 times the size of the Earth, which makes it the mother of all storms.
We've known about the Great Red Spot in Jupiter's southern hemisphere for more than 300 years.
When Galileo invented the telescope, within a few tens of years, people had seen the Great Red Spot, and it's still there.
Familiar yet mysterious. Nobody knows how the Great Red Spot formed. But scientists are finally probing below Jupiter's cloud tops to uncover more about this enormous alien storm. The storm is powerful. With wind speeds of 300 miles per hour, it rises miles above the surrounding clouds. On Earth, we have storms that seem similar, though smaller and milder. Hurricanes, also known as cyclones or typhoons, depending on where they form. They're our most destructive weather systems. But is there more than just a passing resemblance between Earth's cyclones and Jupiter's red spot?
When you look at the Earth from space at a hurricane, it's this big swirling pattern. It's round, it rotates. Jupiter's big storms look big and round and cloudy and they rotate, but there the similarity ends.
In a hurricane, there is an internal core, which is called the eye of the tropical cyclone, and that's a region of very calm winds and no clouds, and usually has a size of about 10-20 kilometers in diameter. And then away from the eye, there is the eye wall. Those are really cloudy regions with a lot of rain. And as you move outward, there is a whole region of about a couple of 100 kilometers with very, very strong winds and very strong rain.
Hurricanes draw power from heat in our oceans. But Jupiter has no oceans, and the sun isn't close enough to power a storm as big as the Great Red Spot. So where does it get its strength? Part of the answer is Jupiter's size. It's the largest planet in the solar system, almost as big as all the other planets combined. This mass generates a very strong gravitational pull, which in turn creates interior heat that rises to the surface. Another piece of the puzzle may be Jupiter's hypersonic rotation. Despite being much larger than Earth, Jupiter's day lasts only 10 hours. In other words, it spins incredibly fast. Could energy from this dizzying spin feed the Great Red Spot?
The weather is really dominated by this fast spin. There's shearing between different latitudes, and that shearing, plus a lot of heat that comes up from the interior of this very massive object, 290 times the mass of the Earth, leads to very violent storms.
Both Jupiter's and Earth's storms spin around in a familiar spiral shape. On Earth, it's because of an effect called the Coriolis force.
I'm sitting at the North Pole, and I want to throw a ball down to a friend who's in Los Angeles. And so if I threw the ball in that direction, the Earth rotates, and the ball will end up in the middle of the Pacific rather than in Los Angeles. So it's like if the trajectory was deflected to its right. And that's what we call the Coriolis force.
This force spins storms clockwise in our southern hemisphere. But there is a stark difference between Earth and Jupiter. The Great Red Spot is in Jupiter's southern hemisphere, and yet it spins counterclockwise. This is because of some other powerful winds.
It's bounded by jets, which are moving in opposite directions. And so like a cog between two conveyor belts, they're just feeding energy and momentum into the system.
Jupiter's complex jet streams spin the storm into organized chaos. But the greatest difference between Jupiter's red spot and our storms may be Earth's solid surface. Once a hurricane hits land, it comes apart pretty fast.
Where they come over land or over mountains, their behavior is very different from where they form over the oceans, and over warm oceans in particular, where we get hurricanes. And on Jupiter, there's obviously no solid surface.
With no land mass to stop it, the Great Red Spot just keeps on spinning and spinning and spinning. Scientists hope to learn more about our weather by continuing to study the storm.
On Earth, there's a limit to how far ahead you can predict the weather. On Jupiter, we can forecast where the red spot is going to be months in advance. It's practical value to understand what makes weather on Earth so unpredictable, and aspects of the weather on Jupiter are much more predictable.
Unpredictable or not, Earth's weather never gets as violent as on Jupiter. That's lucky for us, because if we shrank the Great Red Spot down to fit on Earth, we'd be in for disaster.
On the Earth, we go up to Category 5 hurricanes, let's think about Category 10 hurricane here. Not much would be left.
Alien storms are vastly different everywhere you go in our solar system. Even our next-door neighbor, Venus. They say we're sister planets. Lucky the resemblance doesn't include weather. Otherwise, we'd get seriously burned. Venus may be our nearest neighbor, but somehow its weather is radically different from ours. The second planet from the Sun is a cross between a toxic waste dump and Death Valley, but even worse.
So it's almost a planetary definition of hell.
The temperature is 900 degrees Fahrenheit. The pressure on the surface is the same as half a mile below the Earth's ocean. And if that's not enough, the upper atmosphere of Venus is choked with sulfuric acid clouds and winds clocked at 250 miles an hour.
To get a comparison for Venus, the best thing to do is climb inside of your oven and crank it up. And then in terms of pressure, you're talking about deep sea diving. It's like nothing. There's nothing comparable on the Earth. It's just a very, very extreme object.
On Venus, there's just no escaping the heat.
If you built up a hot spot on Venus, the massive atmosphere would just carry that heat away and spread it around.
But Venus shines so brightly in the night sky because its thick clouds reflect almost all the sunlight it receives. In fact, some early scientists assumed Venus would have moderate Earth-like temperatures.
When we went by Venus in 1962 with a spacecraft, we thought we would find a surface at 90 degrees Fahrenheit, sort of like Miami, Florida.
We were dead wrong. Something else must be at work on Venus. But what? So why doesn't Venus cool off the same way Earth does?
On the Earth, for example, we have sunlight coming in, hitting the surface of the Earth. The Earth warms up a little bit, but the oxygen and the nitrogen in the atmosphere don't impede the light, so when it gets released out in the infrared, it goes right through the atmosphere and leaves and goes into space.
But on Venus, the atmosphere is 97% carbon dioxide, giving a whole new meaning to the greenhouse effect.
It becomes very, very hard for the surface to get its energy out.
So Venus really taught us a lesson, that if you have a blanketing gas, a greenhouse gas, it can warm up the atmosphere tremendously.
But why does Venus have so much more CO2 in its atmosphere than Earth? The two have much in common. They're even called sister planets. They're almost the same size, have roughly the same amount of carbon, and billions of years ago, both had lots of water. But eons ago, their paths mysteriously diverged. On Earth, water fostered life.
The Earth has most of its carbon in life forms, in the trees and the animals. But if you took all that carbon that's in the near-surface rocks and burned it up or released it, you would then create an atmosphere very much like Venus.
Venus's close proximity to the sun made it too hot to sustain liquid water. Instead, its water evaporated into the atmosphere, trapping the heat deposited by the sun and creating a runaway greenhouse effect. Once in the atmosphere, the water molecules were exposed to solar ultraviolet rays that broke the molecules apart.
It really wasn't recognized by the scientific community how important the greenhouse effect was prior to going by Venus and seeing this amazing place where it was 900 degrees Fahrenheit, not 90.
It took several doomed missions to Venus to figure it out. Starting in the 1960s, both the United States and the Soviet Union sent unmanned probes past the planet and down to its surface. It didn't take long before Venus crushed and burned them. Then, in 1981, the Soviet lander Venera 13 set a record for survival on the surface of Venus. 2 hours and 7 minutes. It was able to take pictures and samples of the surface before being overcome by the heat.
You're sitting there with this 900 degrees Fahrenheit heat all around you. It's going to get in there and bake you after a while.
Scientists one day hope to send a probe to Venus that can survive its hellish environment, to help us confirm our theory of how this planet went astray. Because if circumstances were just a little different, our sister planet might just be our twin. Remove our atmospheric shield, and you're on the road to hell.
As soon as you're heated up to something like 400 degrees or so, you'd probably start getting some smoldering smoke, and way before it gets to 900 degrees, the Earth would burst into flames because of all the oxygen around.
Once the oceans boiled away, the carbon locked in rocks on the ocean floor would cook, and over millions of years re-enter the atmosphere.
Probably if you came back to the Earth system after this happened, you'd find a planet looking much like Venus.
We're a long ways away from such a drastic change, but it's sobering to look at Earth's sister planet when the sister planet went on a very different track than we did.
So cosmic forces turned Venus into a planetary barbecue. But on this violent, stormy world, time and the elements have produced some of the strongest thunderstorms ever measured. Welcome to Saturn.
Probably the fact that there's more water in the atmosphere, pound for pound, on Saturn makes the storms bigger.
More water droplets means more friction, which means bigger lightning bolts. But energy emerging from the planet may also contribute to the power in Saturn's thunderstorms.
It turns out that where Lightning Alley is on Saturn is a place where the winds are flowing the slowest. If you go deep down in the atmosphere, you'll see the same winds as you do up high. It's a place where the energy being released deep down below can make it on up to the upper atmosphere without being sheared apart and it allows storm systems to be organized.
Earth's atmosphere isn't built that way. So, as violent as our storms get, they're nothing compared to the systems on Saturn. Even a run-of-the-mill mega thunderstorm on Saturn would devastate us here.
A Saturn-sized thunderstorm on the Earth would mean a thunderstorm that grows to cover all of North America and presumably has very strong winds and rain. This is something that's unprecedented on the Earth.
Saturn's hyper-violent thunderstorms are proof that our planetary neighbors have weather far more ferocious than ours. But the laws of physics that create Saturn's storms are the same laws that create our own weather. Massive dust storms, unrelenting winds, killer lightning, powerful hurricanes, and searing heat.
Today I want to talk about explained but nonetheless mind-warping facts about phenomena and objects in the universe. Some of them are actually downright spooky. And I'm going to begin with the basic constituents of matter. You know, by 1900, the very existence of the atom was still a hypothesis. Atom, you may remember, is Greek for indivisible. 1897, the electron, the very first atomic particle, was discovered by British physicist J.J. Thomson. There it is, discovered. No other particle is known. So what does he say about the electron? He says, in toasts that he would give at dinner time, he would say, "To the electron, may it never be of any use to anybody." So what is an electron? We can measure its charge. You can measure its mass. It actually has something that we call spin. And you can measure its effect on other particles. You can measure all of this. But you know something? The electron itself has never actually been observed. Not ever. In fact, the electron is smaller than anything ever measured ever. Whatever is its size, we have yet to figure out how small it is. And as far as we're concerned, it could be infinitesimally small. That's the electron, the particle that we all know and love. Then you've got the proton, discovered in 1911 by New Zealand physicist Ernest Rutherford. How did he discover it? Well, he beamed helium nuclei. So what's a helium nuclei? It's got 2 protons in it and 2 neutrons, but the neutron wasn't discovered yet, but he knew they were the nuclei of helium atoms, sometimes called alpha particles. He hammered gold real thin and suspended it in a thin gold foil curtain. And he sent helium nuclei, alpha particles, into that gold foil. And he checked to see how many of them are deflected, how many of them go straight through. And what did he find? Nearly every single helium nucleus that he sent into that gold foil passed right on through unperturbed. This is solid gold foil, what we would call solid. He would conclude that atoms are mostly empty space, a staggering amount of empty space. In fact, the volume of the atom is a quadrillion times larger than the volume of the nucleus itself. If you want a sense of that scale, take a BB, stick it in the pitcher's mound of a baseball stadium, and the size of the BB is to the stadium as the size of a nucleus is to the atom. So Rutherford, who discovered this, he is rumored the next morning after he realized that matter is mostly empty space. He is rumored to have been afraid to step out of his bed onto the floor out of concern that he might pass through the solid floor of his residence. This is the consequence of being the very first person in the world to know some truths about the nature of matter. Another particle. We have electrons, protons, neutrons. That was discovered in 1932 by British physicist James Chadwick. Neutron. That took a little longer to discover because it has no charge. And if you have no charge, it's hard to find ways to interact with it to discover that it's there. We would later learn that the neutron and the proton, they themselves are not fundamental, but they're made up of quarks, 3 quarks each. Well, if they each have a charge, an electron is -1, a neutron is neutral, a proton is +1, and if the neutron and proton are composed of quarks, then the quarks must have fractional charge. In fact, they do. The quarks come in charges of 1/3 and 2/3. These are the charges that quarks have. And you can combine them in different ways to recover either 0 charge or the charge of +1 for the proton. Quarks were theorized in 1964 by American physicist Murray Gell-Mann and George Zweig. 4 years later, they would be discovered at the Stanford Linear Accelerator Center, 1968. 1968, the most turbulent year in American history since the Civil War. Assassinations, Tet Offensives, Vietnam War. Yet, the march to understand the universe persisted, such as the challenges of a nation. Where did this word come from? Murray Gell-Mann had been reading James Joyce, Finnegan's Wake, and he came upon a passage, 3 quarks for Muster Mark. Sure he has not got much of a bark, and sure any he has, it's all beside the mark. Knowing that 3 quarks are in your neutron and your proton, he figured, why not call them quarks? There are 3 regimes of quarks: low energy, medium energy, and high energy. Low energy ones, we call them up and down, 2 quarks, up and down. Medium energy, charmed and strange. High energy, top and bottom. The total number of quarks in this universe are 6. 6 quarks. So Murray Gell-Mann got it wrong. He thought there were only 3, but there are 6. They're still called quarks. All right. Here's what's spooky about quarks. You can never isolate one in free space. You can't. You know why? Because here's a pair of quarks that are bound together, and you're gonna go try to separate them. So, all right, I challenge you to do that. So you grab one side and the other, and you start pulling and pulling and pulling. Well, quarks have a particular property, that the force that brings them together gets stronger the more you pull them apart, not weaker. That's spooky unto itself. But here's what happens. You pull them together so far, you're pumping energy into it at such a level that the moment you successfully separate them, the energy you put in them spontaneously becomes another pair of quarks. So the one you pulled out here, another quark gets manufactured out of the energy you pumped in. E equals mc squared, the equivalence of mass and energy. The other quark, the energy you pumped into that, it makes a second quark. So you start it with 1 pair, you separate them, now you have 2 pairs. And at no time did you ever isolate a single quark. That's how quarks behave. They don't ever want to be lonely. That's spooky to me. Quarks. Always in pairs. Now you got another particle, the neutrino. That's a spooky one, the neutrino. That was predicted in 1930. It would take 26 years to discover it. Why? Because the neutrino hardly interacts with anything. It comes out of a nuclear reaction and the particle just escapes. It is fast moving, it is ghost-like. It's made in abundance in the sun's core. And it's made in even higher quantities when a star dies in an explosion, a supernova explosion. Now, the neutrino hardly ever interacts with matter, and I'll give you a quantitative measure of that. If you take an entire light year of lead, a light year of lead, that's 5.8 trillion miles of lead spread out through space. Go ahead, get that. And send a neutrino through one end. You might block the path by the time your light year of lead has been traversed. That's how unsociable neutrinos are. And because of how many are made in the center of the sun, you can calculate how many these are. 65 billion neutrinos pass through every square centimeter of your skin every second. All from the sun. Neutrinos, ghost-like particles, no charge, traveling nearly the speed of light. So these particles we don't experience them in everyday lives. They reveal themselves to us in particle accelerators. So you can say, oh, that doesn't make sense. Oh, that doesn't. Well, how can it not have no size? None of that makes sense. They're under no obligation to make sense because they've been revealed through the methods and tools of science which themselves transcend your senses. And so some of the spookiest features of modern physics reveal themselves as we probe matter on its deepest level. One of the towering great achievements of the human mind and our understanding of the universe is Einstein's theories of relativity. It's actually, the tenets of it are quite simple, almost scary simple. It makes only two assumptions: that the speed of light in a vacuum is constant no matter who is doing the measurement and no matter what direction you are moving or how fast. You'll always get the same measurement for the speed of light. That's assumption one, which, by the way, experiment has shown to be true. Assumption two, that the laws of physics as you measure them are the same for every observer who would be doing the measuring, provided you are on a vessel that's either moving at a constant speed or not moving at all. Those are the only two tenets that you have to buy into. And all experiments have shown that both of those two tenets are correct. Given those two tenets, extraordinary, spooky phenomenon derive from them. For example, as you travel faster, or if you find yourself in the vicinity of a higher source of gravity, time ticks more slowly for you than it does for other people who are not. It's not just your clock, it's everything about you and your environment slows down. You don't notice this because everything is slowing down, including your neurosynaptic thought rate. So it goes unnoticed to you, but it's patently obvious to everybody else observing you. And this leads us to the famous twin paradox. So here's how it works. Let me get a pair of twins. All right? They're born the same time, they're the same age. And now one of them I will send off at 90% the speed of light. And the other I'll keep down here on Earth. So we can ask, how do their aging rates compare? Okay? Turns out, this twin that I've already sent, his clock ticks 44% as fast as this twin's clock, our clock here on Earth. So, this twin is aging more slowly than this one. That's at 90% the speed of light. Let's pump it up some more. How about 99% the speed of light? Now the time ticks at only 14% the rate, as it does back here on Earth. How about 99.9%? We're getting closer and closer to the speed of light itself. And at that speed, the clock ticks only 4.5% as fast. So, What does this mean? I'll tell you what it means. This twin that travels for 5 years and comes back, if they went at 99.9% the speed of light, after 5 years, they're 5 years older. We have aged 110 years. It's called the twin paradox. It's only a paradox if you think about it in sort of classical terms. How could that be? But in relativity, there is no paradox at all. That is a fundamental feature of what happens when all you do is presume that the speed of light is the same for everybody and the laws of physics remain constant. That whole phenomenon is called time dilation. And if you take it to the limit, let's take it to the limit. Is there anything around that actually moves at the speed of light? Sure is. It's not a material matter. It's light moves at the speed of light. Photons, the carriers of light, move at the speed of light. So, if time slows down as you approach the speed of light, then the equations tell us that at the speed of light, time stops. That means if you were a photon, time does not pass for you at all. Now that has some freaky, spooky consequences. What that would say is that the instant a photon is emitted anywhere in the universe, typically they come out of atoms or they'll be sent out by a star, the instant it is emitted, it gets absorbed at its destination, if you're the photon. For the rest of us, we're watching it move at the speed of light across the galaxy or across the universe. But to the photon, time does not elapse. Hundreds, thousands, millions, billions of years of our time are zero time for the photon. And I've reflected on this often. I've been on mountaintops with my telescope and a detector, observing the center of the galaxy. That was the subject of my PhD thesis. What was going on 30,000 light years away? And I kept thinking, these are photons that have been journeying for 30,000 of my years. And they come through the vacuum of space, enter Earth's atmosphere, come down, they happen to hit my telescope mirror, focus down on my detector, there they are. And I'm using their existence to help me deduce the nature of the galaxy. Then I asked, did the photon want to hit my detector? If it didn't, where would it land? There's some people laying out on a beach. Some of these photons are hitting people's bottoms, okay? I don't know if that... Imagine being emitted and that's the first thing you hit. Someone's rear end who's sunbathing on a beach. So I felt kind of proud that I could take some of those photons and use them to deduce the nature of the universe, because plenty of other photons would have passed Earth by in search of where they would end up becoming absorbed. And so, such is the plight of the life of a photon. Because in fact, since time doesn't tick for it at all, it actually has no life. All that exists about it is what we say, what we do with it when it arrives here. That's a curious duality in the existence of this particle. From its own point of view, the universe goes by in an instant. And for us, we bask in the time it takes for the photon to reach us. What else is spooky in the universe but true? Quantum physics. That wins all prizes for just the weirdest things about nature we have ever discovered. This is a theory of the universe that's been around since the 1920s. In that decade, which by the way was a watershed decade for physics, that's when Edwin Hubble, not the telescope, the space telescope, but the man after whom the telescope was named, that's when he discovered that our galaxy, the Milky Way, is just one of countless other galaxies in the universe. And in that same decade, he discovers that those galaxies themselves are rapidly receding from one another, telling us that the whole universe is expanding. Had they given Nobel Prizes to astronomers back then, he would have gotten 2 at least two. Edwin Hubble, he started out as a lawyer and then became an astronomer. Interesting character in the history of my field. In any event, that decade gave us quantum physics, which, it turns out, is the most successful theory of the universe ever put forth. There is no known edge of its applicability to any problem we've ever encountered. It has worked in every place we've ever used it. Its predictions have shown up to be true every time we've ever invoked them. Meanwhile, there are other what we call successful theories like Newtonian gravity. It works to a point, but then you need Einstein gravity to take it to regimes that Newton never experienced. Quantum works everywhere, and there are weird things that go on. Particles also exist as waves, and they can pop out of existence and into existence somewhere else. They don't exist in any tangible way. They exist statistically. Very weird things go on in quantum mechanics, and it is a regime that falls outside of our common sense. So you can't invoke your common sense to decide that what it is you just learned should or shouldn't be true. Take, for example, a sphere that I might pass through a sheet of paper. That's an interesting experiment. Suppose my entire life is just that sheet of paper. What will it look like to me if I pass that sphere through it? First, I see a dot. That's the point of contact of the sphere with the page. I don't know that there's a sphere. I just see the page and there's a dot. That dot, what next? It becomes a small circle, and a bigger circle, and a bigger circle. The circle gets to the diameter of the sphere. After that, it gets smaller and smaller again, ultimately becoming a point and then disappearing altogether. That's just weird. If I describe that to you, and I don't know that a sphere is passing through the sheet of paper, you'd think I was crazy. So I'm left wondering, and I'm not alone in this state of mind, whether so much of what we see as quantum mechanics that defies our common sense, that is just crazy, loopy, weird, is actually some sensible thing going on in a higher dimension that happens to be passing through our low dimensionality. I stay awake at nights wondering that. An interesting feature of quantum physics is called tunneling. Well, we learned that a particle can also be a wave. Well, a particle has an existence in a spot. Right? Here's a particle right now. But when you think of it as a wave, the wave can be in multiple places at once. And when you measure that wave, it becomes a particle. And if you measure that wave over here, the particle shows up over here. If you measure the wave here, the particle shows up here. So there's a chance you can measure the particle in any location in the vicinity. Turns out the particle can tunnel through a barrier that it would not otherwise be able to penetrate. That's like me standing next to a mountain, disappearing and reappearing on the other side of the mountain without having to cross over it and invest any energy doing that at all. That's called quantum tunneling. Turns out, the very mechanism that drives the energy production of the sun requires it. We had known long ago what the temperature of the center of the sun is. It's about 10 million degrees, give or take. 10 million. At those temperatures, particles are moving very fast. Hydrogen atoms. The sun is made of mostly hydrogen. And their nuclei are protons. They're moving fast. Protons want to resist one another. They're the same charge. And most of the time they do. But in order to fuse them, in order to engage in thermonuclear fusion, thermo is hot, nuclear is the nucleus, fusion is bringing them together. In order to engage in thermonuclear fusion, they have to overcome that repulsion, get close enough to each other until a strong force takes over. In fact, we call it the strong force, the strong nuclear force. That's an attractive force that bonds nuclear particles together, creating bigger and bigger atoms. How do you do that if it's not hot enough to accomplish it? There is a famous British astrophysicist named Sir Arthur Eddington. He said, 10 million degrees is not hot enough, folks, but that's still the hottest place in town. So if we're going to cook elements, figure out a way to do it in there, because I don't know any other place. Turns out, tunneling was the answer. Something discovered in the 1920s when quantum mechanics was fully fleshed out. Some of these nuclei will tunnel across that barrier even though the temperature isn't high enough to accomplish this. Some of them tunnel through the barrier, they bond, they make the heavier elements, and energy is released. The star is born and the star is sustained. Beyond light and the colors that it makes, what is most astonishing to me, and we've known about this since 1905, so this is not new, but every day I think about it, my jaw drops open. And that's the equivalence of mass and energy. An equation first written down by Albert Einstein in 1905. You learned it in elementary school. E equals mc squared. The c is the speed of light squared. It's a constant. Don't worry about that. All that matters in that equation is that energy sits on one side and mass sits on another. And we've known about this in Cold War politics because our entire nuclear arsenal depends on that formula, creating energy out of matter in a bomb. Okay, and the sun does it every second of its life. So does every star you see in the night sky. We don't have an everyday experience with E equals mc squared. That's a good thing. But if we had very sensitive measuring devices, we would. For example, if I take a spring and I stretch it, I'm actually pumping energy into the spring to hold it in a stretched position. If you figured out how to weigh that spring in before and after situations, you'd find out that the stretched spring weighs more than the unstretched spring because I pumped energy into it, and that energy has mass. The energy has mass. It'll show up in a spring, it'll show up in a rubber band, it'll show up when you stretch a rubber band, it'll show up in chemical powders like gunpowder that's stored energy in the molecules of gunpowder. Gunpowder weighs more because of that stored energy than it otherwise would if you broke apart those molecules. Not only that, gasoline weighs more simply because it has stored energy. And so when I think of all that drives the universe, when I think of what makes the universe tick, you part the curtains, what's behind it all, you will find the equivalence of mass and energy. That equivalence of mass and energy drove phenomenon in the early universe, in the Big Bang itself. It drives the energy production in every star you see in the night sky. It was responsible, like I said, for the geopolitics of the Cold War. All by that one little equation, making so much sense of what goes on in the world. And of the many things that prevent me from getting a good night's sleep, one of them is there another equation like E equals mc squared just beyond our reach? Because we are still steeped in profound ignorance of what's going on in the universe. There's a lot we know, proud of that, but there's even more that we don't know. Is there some equation like E equals mc squared that we haven't seen yet? If it's there, is it just out of our reach, or is it not just out of our reach? Do we have to climb several mountains before we even get to the point where we see the next equation that can transform the next generation's understanding of how this universe works? I don't know. But what I do know is E equals mc squared explains so much of what's going on in this universe. It actually makes us feel a little cocky about it. It's like, yeah, we're there. We got it. But the March of Science tells us Just when you thought you understood something, the universe throws you a curve.